So let's talk about conservation of energy. Gravity is a conservative force, which means when an object is under the influence of just gravity, the total energy within the object will remain the same. This energy can be converted from one form to another, but the grand total value will stay the same. So here's an example of a very attractive gentleman sitting on the edge of McAfee's Knob. If he falls off, he will fall roughly 40 feet. This is equivalent to 12.2 meters. And the question's asking how fast he'll be moving just before hitting the ground. Now, this is a question you could have answered back in one of the first modules with the equations of motion. However, a lot of times it's easier to look at this as a conservation of energy problem. When dealing with conservation of energy, you want to look at your total energy before and your total energy after and set them equal to each other. My total energy is going to be a combination of my kinetic and potential energies at any given moment. So my total energy to begin with is my initial kinetic plus my initial potential, and I'm going to set that equal to my final kinetic plus my final potential. I can substitute in the appropriate equations for each type of energy, and now I can start plugging in some values. Well, since I wasn't moving initially, I start from rest. That means my initial velocity is just 0. Cool. By the time I land on the ground, my height has changed essentially to 0. So since both of those terms are going away, I'm left with just my initial potential energy equals my final kinetic energy. And my mass actually doesn't matter because it divides out from both sides of the equation. The question's asking how fast I'm moving at the bottom, so I need to solve for my final velocity. And it just comes to the square root of 2 times g, which is 9.81, times my initial height. Now all I got to do is plug in the value for my initial height, and I am done. So right before splatting into the ground, I'm moving at around 15.5 meters per second or so. Just for reference, that's approaching 35 miles per hour, so that's gonna hurt a fair amount. Like I said before, you could have solved this with your equations of motion. What I like about conservation of energy is that everything is a scalar, so you don't have to worry about direction. If instead I had done a running leap off of McAfee's Knob, then based on the kinetic energy that I had at the beginning, along with the potential energy, you could have calculated how fast I'd be moving right at the end. Initially, with your equations of motion, you would have had to divide everything into x and y components, solve the motion in the x direction, solve the motion in the y direction, bring it all back together. With conservation of energy, you can just do it all in one step.